Swayam Prabha. Digital India. Educated India.
Hello and welcome back. We are discussing basics of building construction, and right now we are dealing with the first module, which is on foundation. In the previous lecture we had studied shallow foundation and its various subtypes. Today we are going to continue this discussion and further elaborate on shallow foundation, specifically in the case of black cotton soil. Before I begin, let me just slightly recap what we had discussed in the last lecture. So we had studied foundation and its subtypes, that is, it can be shallow and deep. We will be discussing deep foundation separately in a subsequent lecture. In shallow foundation, we had also studied that it can be further categorized into four major types: spread footing, combined footing, strap footing, and mat or raft foundation. So those were the subtypes we had seen, and we had discussed how they could look, what are its component parts, and in which context they are applicable. So we are today discussing again further on a specific type of foundation in a soil which is quite challenging, that is black cotton soil. Now, why is this particular type of soil challenging? Black cotton soil is an expansive form of soil. So it has the typical characteristic of shrinkage and swelling. Now this happens due to moisture movement throughout the various seasons, and this type of soil is specifically known for having very poor bearing capacity. During the rainy season, the moisture penetrates into these soils, as a result of which it swells up, mainly because this type of fine-grained clay, it has grains in the form of platelets or sheets rather than in a round format. So when moisture enters into these platelets, in hydrostatic pressure, the particles separate out, increasing in volume. Now this increase in volume, which happens in the rainy season, is called swelling. Similarly, in the summer season, just a different contrasting environment will be created, where there will be a lot of shrinkage happening in the soil. Now if swelling or shrinkage is not restricted in black cotton soil, it is going to cause significant damage to the footings and eventually the superstructure as well. So the swelling pressure, which will be acting in the upward direction, is going to cause damage to the footing and then eventually to the superstructure, resulting in the formation of cracks in the walls, and it can also damage other structural elements such as lintels, beams, slabs, etc. Now during the summer season, the moisture is going to be coming out of the soil, causing the soil to shrink. Now when this soil shrinks, it reduces in volume significantly, and it causes a pull down action, resulting in the formation of shrinkage cracks. They are also known as tension cracks, which can be as much as 10 to 15 centimeters wide at the ground surface, and they can go as deep as 2 meters. Now these cracks are going to result in a loss of support underneath footing and will cause very high settlements in the structure. In the previous lecture, we had discussed how settlement in our buildings can cause major damage, and that is one of the functions predominantly that footings will have to take care of. Now some expansion and shrinkage has to be accommodated within this black cotton soil in order to prevent the formation of cracks in the superstructure walls. Now for this, special attention has to be paid to certain aspects of foundation design, which we are going to discuss today in detail. Various types of foundation can be used in black cotton soil. We are going to discuss each of them one at a time. The first is a simple strip or pad foundation. Then we are going to discuss an example of pier foundation, followed by under-rimmed pile foundation. Now though pile foundation is going to be discussed in detail in deep foundation lecture, we will take a brief look at under-rim pile foundation because of its particular suitability in black cotton soil areas. So the first example is that we can apply strip or pad foundation with some special considerations in a black cotton soil area. So if we are dealing with medium loads, a strip foundation can be done for the walls and pad foundation for the columns, where 60 centimeter of cohesionless sand is placed right below the concrete and is compacted. Now this helps us to accommodate the swelling pressure which is created in the soil due to the seasonal moisture content change. Now here we can see some examples of figures which depicts how black cotton soil footing can be designed. We will discuss that. Now what we are trying to do is we are trying to create alternate layers of sand and muram so that we can create an accommodation for this change in volume that is happening in the soil. So 25 to 30 centimeter of concrete strip is laid on top of subsequent layers of sand or muram or ballast. So the first example, which is figure A, is a simple sand fill in which we have created a certain amount of sand in a pit within which our footing is cushioned. So what we are trying to do is we are creating this particular footing within a cushion of sand from all sides, which will help us accommodate the swelling pressure that is building up seasonally. In addition to this, please note there is something called plinth protection which is added at the ground level sloping outwards. This is also very important in the context of black cotton soil. If we are dealing with a situation in which the swelling pressure is slightly high, then we can either use the example given in B or C, in which we can have alternate layers of muram and ballast along with sand to provide additional cushioning from the swelling pressure that is being generated. Now in case we are dealing with a soil where very high swelling pressure and very high shrinkage properties are also there, in that case we can use sand fills and concrete blocks at the bottom. In each of these examples, we are going to introduce a pipe at regular intervals, which will be starting from the base of the plinth area, so that we can keep adding sand over time. So during the long life of the building, if the sand shifts underneath this concrete base due to the swelling action and the shrinkage action that is happening seasonally, we can keep adding sand even in the later years for our foundation to keep functioning properly, given the special and unique characteristics of the black cotton soil. So if we are in a particular place where the black cotton soil only is very slightly deep, that is, it is on the top layer of the soil and it's not more than 1 to 1.5 meters, it is best to remove the complete layer of black cotton soil and deal with the non-expansive soil underneath to build our structure. So if possible, it's best to remove it. But if that depth of the clay area is very large, then the foundation of the footing will have to be made within this soil itself. So the special considerations that we discussed are going to become applicable. So sand and muram layers can be placed underneath the footing to give the cushion to it, and the construction should be started in the dry season preferably, because in that case we are dealing with the lesser volume and the challenges of construction will reduce significantly. Suitable plinth protection, as I mentioned earlier, will have to be applied on the external wall at the ground surface, and it has to slope away from the wall so that the moisture does not penetrate the foundation during the rainy season, because when expansion happens, it is possible that the water can actually enter this area that you've created to cushion your footing. So to prevent that, plinth protection is very much required in this context. The second type of foundation that we can use in black cotton soil is pier foundation with arches. So the name is pretty self-explanatory. What we are doing is we are creating piers at regular interval, and above this, with the help of arches and a level base, we are going to create a surface on which we can further build our superstructure. So the piers are dug at regular intervals and it is filled with cement concrete. We will ensure that this pier actually reaches the strata of soil which is got a good bearing strength. So we are going to go as deep as necessary to reach the bearing strata anchor our building with the help of these spires at that level, and above this start building our structure. So these spires are connected to each other with the help of masonry arches. We can also use concrete to build these arches. You can see this is in cross section and this is in elevation. We can see how the arches are spanning between the piers, connecting each of them. Now once these piers are created, we will provide a concrete beam above this arch so that we can get a level surface, a straight surface on which we can start building our superstructure, because obviously we cannot build our superstructure on a curved under surface. Now these arches are constructed such that there is a gap above the ground level. Now why do we need this gap? Because seasonally we have learnt that black cotton soil is going to undergo shrinkage or expansion. So this vertical movement of soil, which is happening due to the change in volume of the soil due to moisture retention, that has to be accommodated within this gap. So we are going to have to leave significant amount of gap between these arches and the concrete beam from the ground surface, so seasonal variations in the soil volume can be accommodated. The third type of foundation that is applicable in black cotton soil is underreamed pile foundation. Now this is a special type of pile foundation which is named such because underreaming tools are used to create this type of pile foundation. Now pile foundation is a type of deep foundation. That means its width is less than its depth. If its width was equal to less than its depth, then it would be called a shallow foundation. If the width is far less and the depth is greater, in that case it will be called as a deep foundation. Now pile foundation will be studied in detail. We will also study underream pile foundations construction in detail in the chapter when we are dealing with deeper foundations, but in this case we are just taking a quick look at what underream pile foundation is and how we are creating it for black cotton soil. Now underream pile foundation is applicable to a depth of 1 to 6 meters. It has bulbs at its lower end. It helps us to anchor the foundation to the ground because this bulb is placed at a critical depth where the bearing capacity of the soil is more. We are able to anchor our building with the help of these bulbs. Now these bulbs are created with the help of underream tools. Now 15 centimeters to 50 centimeter in dia is usually chosen for these piles and they are suitably placed throughout the building. These underreaming tools are used on site to create the pile foundation in situ itself. Some reinforcement is also given to accommodate the tensile stresses. The pile spacing is about 2 to 4 meters. Now the piles are connected with the help of a rigid capping beam, and above this capping beam we construct the walls of the superstructure. Now the capping beam is about 8 to 10 centimeters above the ground. This 8 to 10 centimeter gap which is left, as you can see in the figure, I am hatching the portion. This will help us accommodate the change in volume seasonally of the black cotton soil. Now this was the discussion on what types of foundations are applicable for black cotton soil areas. That gives us a good idea about the types of shallow foundation that we can apply to most of our structures. Now that we've learned how to identify the type of foundation that we want, only in the context of shallow of course, deep foundation we haven't explored yet. Next we need to know what is the size and shape of our foundation. That is how deep it has to be, how wide it has to be, if it has masonry offsets, how should they look, how should they be distributed. Now these are some of the questions that we are going to have to learn to answer. So for that we are going to learn the different formula which is applicable and how we can solve the numericals for the same. So designing a footing. The first thing that we need to know is what is the minimum depth of our footing. That is our starting point. Now to do that, we can use the Rankine's formula. The Rankine's formula is used to determine the minimum depth of the footing. Now the formula is d minimum, which is the minimum depth, should be equal to q by y into 1 minus sin phi by 1 plus sin phi whole square. Now phi here is the angle of repose. We will understand what that is soon. Q is the total load which is coming in ton per meter square or kilonewton per meter square. Y is the unit weight of soil in kilonewton per meter cube. Now with this formula we can calculate the depth of the footing. Now once we know the depth, what is the next thing we need to know? We need to know the width of the footing. So with the help of the width and the depth, we know exactly the size of the trench we are going to have to dig to create our foundation. Now we know that shallow foundation is also called open foundation because open excavation is required for this type of foundation. So as a result, we need to know the depth as well as the width of this particular trench that we are going to have to dig to be able to fit our foundation in. Now the width of the footing, it will be based on the safe bearing pressure of the soil and also on the superimposed loads. So the base will be equal to W by QS, where this is the superimposed loads and this is the safe bearing pressure of the soil. Now once we know the depth as well as the width of the foundation, we have to start designing the foundation itself. So the first thing we need to know then is the base. This base will be created first within this particular trench. So we need to know what is the depth of this concrete bed so that we can construct this on site, because we already know the width of the footing, we know what capital B will be, but we do not know what small d will be. We have to calculate the same to be able to know what is the concrete base's size. Now d is calculated using the formula a root over 3q by m, where a is the projection beyond the masonry face. So that means it's the offset. Okay, so it is this a. In the figure, this a is the offset from the masonry base. How much is the projection at this level? We need to know this value. M is the safe modulus of rupture of concrete mix, so we will have to know this value. And Q is the net soil bearing pressure. With the help of these, we will be able to calculate the small d, which is how width of this particular concrete base, what is the thickness of this concrete that we are placing at the bottom of our footing. Now once that is known, we will know from the ground level how much of a distance we are going to have to accommodate with the help of our masonry offsets in between, because we know capital D, which was calculated with the help of Rankine's formula right here, and we know what will be capital B, that is the width of this entire foundation, and we also know what small d will be, that is how thick our concrete base is. So capital D minus small d will be the rest of the distance that we are going to have to cover between the ground level and the start of the concrete base. Now that will be done with the help of the masonry offsets. Why do we need those masonry offsets? Because load has to be transferred at a particular angle. According to the National Building Code, we had discussed this in the previous lecture, there is a certain flow through which the load will be transmitted. So we require certain masonry offsets to be placed to bridge this distance between the ground level and the concrete base. Once that is done, we should do a quick check to ensure that based on the angle of load transfer, whether the depth that we have designed is correct or not, it is safe or not. So the formula for that is given below. This will help us determine whether the foundation depth that we had designed using the Rankine's formula is correct or not, safe or not for our foundation. So these formula are going to help us walk our way through designing a footing. We will take a look at a numerical to understand how to apply each of this formula, but before we do that, let's understand a little bit more in depth what is happening in each of these calculations. So the depth of the foundation by the Rankin's formula, a quick recap again. So here we have d minimum is equal to q by y into 1 minus sine phi by 1 plus sine phi, where phi is the angle of repose. Now what is the angle of repose? Angle of repose is a particular angle beyond which any loose material, any granular material, if it is piled, it will start slipping. So let's say on a construction site, you have started piling sand and you have placed it in a bit of a mound, like a little hill. So there will come a point, if you keep pouring sand on top of, there will come a point where it will start slipping. This is the exact angle which is called the angle of repose. So right at the point when the slipping starts happening, that is the angle of repose. The Q here in this formula is the intensity of the load which is being placed at the base of the footing. So this includes the superimposed loads which are coming from the superstructure, as well as the self weight of the foundation, because the foundation itself carries certain weight which is going to be carried by itself. So that load intensity we are going to have to calculate and ensure that will determine our Rankin's formula's calculation of the minimum depth of footing. And Y is the unit weight of the soil in kilonewton per meter cube or ton per meter cube. Here are some examples. It's a list of the angle of repose for different types of soil. So based on the type of soil that we are dealing with, this is exactly why one needs to test the soil type before starting construction. So you need to know which type of soil you are dealing with to be able to calculate the angle of repose, which you can refer to from this type of a table and fit that into your formula for further calculations. So once the depth is done, we are going to move on to the width of the footing. So the width of the footing is going to depend on the total superimposed loads and the safe bearing pressure which is in the denominator. Now as per the National Building Code, the angle of spread of the load from the wall base, which is here, to the outer edge of the ground bearing has to be at a certain angle. So in case of brickwork and stone masonry, the ratio is half horizontal to 1 vertical. In lime concrete, it is 2/3 horizontal to 1 vertical, and in cement concrete, it is 1:1. So thus N is half and N1 is 2/3 for lime concrete and N1 is 1 for cement concrete. So when we are dealing with a particular type of material that we are using for the footing base, based on that we can calculate what is the angle or the ratio in which the load transfer has to happen and accordingly design our footing. The check formula, that is to check that the depth calculated by the Rankin's formula is correct or not, that is the safe depth or not, because we don't want to create a footing which is little shallower than necessary. We have to reach the right amount of depth to be able to transfer the requisite load coming in from our superstructure to ensure the safety of our building. So in order to check that, the minimum depth can also be calculated from another angle and then checked with the Rankin's formula. The formula in this case is d minimum equal to half by 2n b minus t minus another component 2d n1 minus 1. Now let's say we are dealing with a situation where N1 is equal to 1, that is the ratio is 1. We are dealing with cement concrete, in that case the ratio would be 1. We can eliminate this part of the formula and just deal with the first part, which is 1 by 2n b minus t. Now in case we are dealing with brick walls, the offset should not be greater than 5 centimeters. So that means this offset, that is every time we are creating a step in the brick masonry to bridge this gap between the base of our wall and the concrete footing base, every time we are creating an offset, it should not exceed 5 centimeter and correspondingly the height of the step should be kept to 10 centimeters. So that means this is 10 and this is 5 centimeter, right? So as a thumb rule, also capital B, which is the base of this entire foundation, should not be less than twice the width of the wall. So let's say if my width of the wall is capital T, so my B at least has to be equal to or greater than 2T. This is a thumb rule. Now, in case of stone masonry, the offsets that we have designed in brick, which was 5 centimeters cross 10 centimeter in height, in case of stone masonry, we can make them 7.5 to 10 centimeter. The height of the masonry correspondingly can be 15 centimeter or 20 centimeter respectively. Now, the depth of the concrete bed that we had seen will depend upon the type of concrete, the projection of the block, that is small a, and the soil bearing pressure. Now, it is found that on the basis of this, the safe modulus of rupture, we calculate what is the small d that should be applicable to our foundation. So, it will depend upon a root over 3q by m, where a is the projection beyond the masonry face, as I have already highlighted in the figure in red. M is the safe modulus of rupture of the concrete mix. So, we need to know exactly what type of concrete mix we are using, and Q is the net soil bearing pressure in kg per meter square. So, with that we should be able to calculate small d, that is the depth of our concrete bed. Safe modulus of rupture of concrete has been listed for some common typologies that may be applicable. Generally, if we are dealing with numericals, we should be given these values to be able to further calculate. So, let us take a look at one numerical and walk our way through the formula we just learned and try and apply that. So, what is our problem at hand today? We have to design a strip footing for a brick wall. The brick wall is 30 centimeters thick and it is 3.5 meters in height above the ground level. The superimposed load is 12 ton per meter. The soil has a unit weight of 1700 kg per meter cube, and the angle of repose is of 30 degrees depending upon the soil type. The safe bearing capacity of the soil is 16 ton per meter square, and the footing may have a lime concrete base which has a unit weight of 2000 kg per meter cube, and the modulus of rupture is equal to 16 ton per meter square. The unit weight of masonry which we are applying in the masonry offsets, that can be taken as 1950 kg per meter cube. So, let us go ahead and try to solve this problem. So, how do we start? We have learned that the first thing we need to do is we need to calculate the depth, capital D minimum of our foundation. Now, what was the formula we had learned? It was Rankine's formula. Now, to be able to use the Rankine's formula, we need to know the unknowns in this particular formula to apply it. Definitely the angle of repose, we know the angle of repose has been provided to us, it is 30 degrees. But what about the superimposed loads that are coming up? So, let us take a look how to calculate the superimposed loads which are coming onto our footing. The first thing we know is that the superimposed load of 12 ton per meter has been applied on our wall. So, per 1 meter there is a 12 ton load coming down. So, that is the first element that we have to take into consideration. But the wall that is there in the superstructure also has a certain self weight which is going to be placed on this footing. So, how do we calculate the self weight of the wall? We know that the width of the wall is 30 centimeter, that is the thickness of the wall, and the height of the wall is 3.5 meters. So, for every 1 meter distance of the wall, the size is going to be 0.3 into 1 into 3.5 if you are doing it in meters. And we know that the unit weight of the masonry is 1950 kg per meter cube. It is provided to us in our question. So, if we multiply all of them, we should be able to get the self weight of the wall per meter, right. So, as per my calculation, that is coming up to about 2050 kg per meter or 2.05 ton per meter, and that is the self weight of the wall. Now, this self weight is going to act along with the 12 ton per meter superimposed load which is coming through the same wall. Now, this is just the superstructure part and the superimposed loads. What about the foundation? The footing itself also has a weight. And where does that rest? On the footing itself. So the footing not only carries the load of everything above it, it also carries its own weight. So let's assume, as a thumb rule, and this is applicable to even the future numericals you solve on your own without my help. So the unit weight of the foundation is going to be about 10% of the total load that comes in. Now this total load includes the superimposed loads as well as the self weight of the wall in consideration. So 12 plus 2.05, we're going to take 10% of that and come up with the unit self weight of the foundation per se for this calculation. That's coming up to around 1.4 approximately ton per meter. So that means the total load which is being transferred to the soil through this wall, through this footing, is going to be the superimposed load component, the self weight of the wall component, and the self weight of the foundation component. And that together is going to give us this number. So before we go to the depth of the foundation, the width of the foundation, that is capital B is equal to W by QS. Very quick formula. Let's apply that first here. So the width of the footing will depend upon the total weight coming in. We've already calculated that, 15.45 ton per meter, and that divided by the safe bearing capacity of the soil that has also been given to us in our question. That was 16 ton per meter square. So with that we are able to come up with a width. Okay, so that's 0.965, approximately very close to 1 meter of width that we require for the footing. So if we are digging a trench at the ground level, it's going to be approximately, or we can call it 1 meter approximately width of this footing. Now let's go to the Rankine's formula, depth of the footing. That's where we started. So the D minimum formula we already know. Here what are our unknowns? We need the Q value. Q is 15.45. That was the total soil pressure that is going to come up every 1 meter. That's because that's amount of weight that we are going to place on the soil because of the superimposed loads, including all the self weight and everything. We also need the value of Y, which is the unit weight of the soil. That has also been provided to us in the question. It is 1700 kg per meter cube, based on the type of soil that we've identified. And the angle of repose has been given to us at 30 degrees. So that's right here. Now when we apply this, the D minimum is equal to 15.45 divided by 1.7. We've converted the units to ensure that we are doing the calculation correctly. The formula was provided with the units as well. So be very careful about the units when applying this formula. Otherwise, we're going to get a very exorbitantly high size of minimum depth, right? So on solving this number comes up very close to 1 meter. So our footing is starting to look very squarish. The pit that we have to create at the base, a minimum depth of 1 meter is required. Now we also know that we have to check our depth using another formula to ensure that it is safe. So if we go about the other formula that we have learnt, which is shown here, we'll try and calculate to see whether the angle at which the load is supposed to be spread on the ground, that we are able to accommodate within this 1 meter or not. We can apply this formula. Now we know that if you're dealing with cement concrete, or a certain angle has to be maintained in our base. If you're assuming that N1 is equal to 1, we're dealing with the same numbers, we can eliminate this part of the equation and just concentrate on the first half. So B minus T divided by 2N. Here B is the width of the footing. This is exactly why we had to calculate the width of the footing in the previous slide before we moved on here, because we need this for this part of the formula. Now the width had also come up very close to 1 meter. It was 0.965. We're going to take it as 1 meter. The thickness of the wall has been provided to us at 30 centimeters or 0.3 meters, and for the masonry part we know that n will be equal to half, which we are going to apply in this part of the denominator. So if we solve for this, so 1 minus 0.3 divided by 2 into half, we will come up with a number 0.7. So that means the minimum depth for the proper transfer of load at the correct ratio or angle would come up to 0.7 meters. Now this is lesser than the minimum depth we had calculated using the Rankine's formula. So we are going to take the number which is higher. So if Rankine's formula is providing us a higher number, we are going to stick to that. We are not going to reduce the size lesser than 1 meter, and that should come up to approximately 1 meter, right? So we are going to stick to 1 meter as the minimum depth of the foundation, and we are going to stick to 1 meter as the width of the foundation. So that means capital B is 1 meter, capital D minimum is also equal to 1 meter. And this was considering that T or the base wall was 30 centimeter in thickness. Now we had also learned another thumb rule, that the capital B, which is the base or width of the footing, should not be less than twice the thickness of the wall that we are dealing with. So the thickness of our wall was 30 centimeter or 0.3, and that means the double of it is 0.6 meter. Again, this is less than 1 meter. So we are safe. According to the thumb rule, we have been able to design the base such that, the width of the base such that it is definitely more than twice the width of the wall. So we are good to go. So now that we've calculated the depth of the foundation, the width of the foundation, we have to actually start designing the base of the concrete base, that is the minimum depth of the concrete base, which was small d, and we also have to design the masonry offsets. Now how do we proportion the foundation into various parts? Now the width has to increase from 30 centimeters at the ground level, which is my thickness of the wall, the capital T. It was 30 centimeters, so that's my starting point. From the 30 centimeter I have to go all the way to 1 meter or 100 centimeter at the base, which is my capital D. Now if we want to make this transition, we are going to have to provide some masonry offsets in between to prevent this change in size from 30 to 100. So how much are we accommodating on both sides? 100 minus 30, that is 70 centimeter divided by 2. Why? Because if we draw a center line through my footing, on each side I am going from half of 30 to half of 100. So this 70 centimeter that I am going to have to cover is going to be divided into 35 on both sides. Now let us say that the concrete projection, that is small a, the offset in the concrete projection will be about 15 centimeters. Let's assume that we're going to have at least 15 centimeters. So we've determined a value for small a. Now hence the total width of the offsets for the masonry portion will have to range from 35 minus 15, that is equal to 20 centimeter. That is the 35 we had to accommodate on each half of the footing, minus 15 which we've assumed as the projection of the concrete base from the base of the masonry offset, that is small a, my offset, and I'm going to have to accommodate 20 centimeters. Now in the previous discussion, when we were talking about masonry offsets, we had discussed how we would keep that as a thumb rule to about 5 centimeter and the height would be about 10 centimeter. So we had determined it would be something like 5 and depth in 10 as we move along. So let's assume that 5 centimeter is that maximum offset that we're going to take. So definitely for 20 centimeters, we need 4 such offsets to accommodate. So we will have 1, 2, 3, 4 steps to accommodate this change from 30 centimeter thick wall to a 1 meter width of a foundation base. Now, because we have been able to determine A as 15, small a as 15, we now need to calculate what will be small d, that is this thickness. How deep should the base of my concrete footing be? So that is calculated using the formula A into root over 3q by m. So A here is 15, we've already decided that, and the bearing pressure on the soil is, we had calculated right in the beginning of our numerical, 15.45 ton per meter square, and the safe modulus of rupture for lime concrete, which we had been asked to use for our concrete base, that would be 16 ton per meter square. Now if we apply that in our formula and do a little bit of calculation, the small d will come up to around 25.5 centimeter. So because we've taken 15 as our offset or small a, and 25.5 is going to be rather difficult to construct on site, so let's stick to a doable number. Let's keep it a little bit more, and 30 centimeter should be a good number for our small d, or the depth of the concrete bed. If we are having a different type of concrete, if instead of lime concrete we were using, let's say, cement concrete, the value of m, or the safe modulus of rupture, would be different. So if we reapply that in the formula, we'll see that the size will come up pretty less, right? So if you were using cement concrete instead of lime concrete, we could have reduced the size of this, or width of this concrete base, to almost half. 14.2 again is a number not doable on site. It's difficult to construct that. We will go for a minimum depth of 15. So in that case, what would have happened is that 15 and 15, that is, the offset is also 15 and the depth is also 15. So it would be a pretty good, n1 is equal to 1. So the ratio that we are expected to maintain according to the National Building Code, we would have still been able to maintain in this case. So we have calculated depth, the width of the foundation, we've calculated what should be the size of our concrete bed, how many masonry offsets are required to bridge this gap. Now pretty much the design of our footing is done, but before we go off to our construction, we're going to do a little check to ensure that what we have designed so far is safe and we made the correct assumptions. Now, what was one major assumption that we had taken in the beginning of this exercise? We've decided that 10% of the total load, superimposed loads that were coming onto the footing, will be taken as the unit weight of the foundation. Now, we need to ensure that that is safe. So, we have to calculate the unit weight of the foundation to ensure that our assumption was safe to begin with. So, now that we've already designed our footing, we can easily go ahead and calculate its total weight. So we know that there are 4 steps. The steps are going to start from the base of the wall. So 30 centimeter and a depth of 30 centimeter here. So that is the first component. We've calculated the plinth wall portion, which is underneath the ground. Then we have the 40 centimeter layer. There are offsets of 5 centimeter on both sides. So that's going from 30 to 40. Again, both steps, so it will go to 50, then 60, and finally 70. So there are 4 steps. So each of the steps we're going to calculate individually. So 0.4 into 0.1, we know that the depth was 10 centimeter each, right? So 0.4 into 0.1 is the first step. Then we have 0.5 into 0.1, that's the second step, 0.6 into 0.1, that is the third step, and the fourth one is 0.7 into 0.1. And all of this, including this plinth wall portion, is going to have a unit weight of 1950, which was given to us in the beginning of the exercise. Other than that, we have a concrete portion, which has a unit weight of 2000. So that is going to be 30 centimeter cross 1 meter. we've calculated that the depth is going to be 30 centimeter and the width is going to be 1 meter, which is capital B. That multiplied by 2000. So we're going to be able to come up with a total number or unit weight of the existing foundation, that is the designed foundation, and that's coming up to 1250 kg per meter or 1.205 ton per meter. Now if you remember, we had started with an assumption that 10% of our superimposed weight was going to be counted as the unit weight of the foundation, and that was approximately 1.405. So 1.4 ton per meter was used in our calculation in the beginning of the exercise. So now that we know that the unit weight is coming up to 1.2, which is lesser than 1.4, so we've made a overestimation, over assumption in the beginning of the exercise. Hence we are safe, and we can say that we've designed a footing which should be carefully able to take the load of all the superimposed as well as the self weight components of the masonry portions as well as the concrete portions in our footing. So this is exactly how we are going to be able to design our footings. Definitely we are dealing with shallow foundation with masonry offsets. Now if we are dealing with a context where we are not going for walls, we are dealing with columns. So for columns we would have to design an isolated pad footing with a concrete base. A similar process will be taken where we will calculate the minimum depth using Rankine's formula, and we will calculate the minimum width, that is capital B, for the base of the footing. In this case, of course, we will have to ensure that the shape of the footing is corresponding to the shape of the column that is resting on it. So if you are dealing with a circular column, we would preferably have a circular base. For a square column, we are going to deal with a square base. For the rectangular column, we are going to have a rectangular base. So keeping with the shape, keeping with the proportion, we will carefully design exactly what will be the sides of our footing and what will be the depth of our footing underneath the ground. So definitely a process very similar to what we've already undertaken will be used. The difference is, in that case, you wouldn't have to deal with the masonry offsets. We would not be proportioning the transfer of the load through various masonry offsets. We are directly making our column rest on a concrete base. So with that, we are ending the numerical, and I hope you have been able to develop a basic understanding of how to calculate the footings. To make a quick recap, what have we discussed today? We have started with what type of foundation is suitable for black cotton soil, highlighting what are the challenges that we deal with in black cotton soil areas. Then we went on to understand what are the formula that are applicable to designing footings and how we can apply them with the help of a numerical. So this is pretty much the end of our shallow foundation portion, which was forming a major component of module 1 of our foundation. So with this, we are ending the first half of the module. Now we are going to continue with deep foundation in the next lecture, where we are going to talk about the various subcategories of deep foundation and what are the types, where are they applicable, how we do their construction, what are the equipment required for them, etc. So thank you for tuning in. Hope to see you in the next lecture.